It's Derek Carter, and in this video, we're continuing on from the previous one. So we're going to look at the second of our two approaches for representing groups of words. So in this video, we're going to look at sequence models, where we're going to process the tokens strictly in the order that they appear. Okay, so let's jump to that. Okay, so let's turn to the second approach, where we're going to process the words as sequence instead of as a bag of words. Okay. So I don't know if we had a real good demonstration, but in lots of tasks, the order can matter. It can give you much better performance, right, than trying to add in a little bit of information, like by using diagrams or something with a bag of words approach. So what if instead of manually crafting order-based features by using like bigrams or trigrams, we expose the model to the actual raw word sequence, right? So it's the first word, second word, third word, and process it, like we did in the previous unit as a sequence or a series, okay? And let it figure out, the best features on its own to represent the input. Okay, so this is basically what sequence models do. So to do that, we're going to pre-process the data, so the output is not a single vector, but is a vector, but where the indices represent the sequence of the word. So this was the index of the first word at index 0. This was the second word, the third token, fourth token, and so on. So then you map those tokens onto a vector to obtain that sequence, and then we're going to look at let's try some recurrent layers like we did before. I'll talk a little bit about what a one-dimensional convolutional network is, and then transformer, although we're going to leave that for the next video here. So first, we need to change our representation a little bit. So we'll have to get a data set that returns the integer sequences rather than that multi-hot encoded vector representation. So this is similar to what we did before. So we are going to be using a text vectorization layer again here to do what we just described. We're going to set a max length of 600. So that means that the sequences that are output from here will have 600 tokens in the sequence. So any review that had less than 600 words will end up being padded with zeros. Anything that had more than 600 words will just get chopped off at the first 600 words, okay? But we're going to use the 1 gram again. So we'll go back to the unigram, which is the default, so we don't specify that here, which, bigrams don't make sense to try and use those in a sequence-based model. So this will look kind of the same as before. So let's be clear what this does. And also we do have to adapt. So we have to build our dictionary, our vocabulary index, the same way we did before, using only the textual inputs for the full corpus here. But the int here means that what's being returned, what's going to be returned from here is an array or a vector of indexes, but in the sequence order that the words appeared in the review, from word 0 to word 599. Okay. So again, just to be clear, let's look at what the output of that is, right? So here we're looking at, so we get, for example, we're using batch size 32. So we get 32 vectors that are size 600 because we cap the size of our sequence to 600, the first 600 tokens, right? So if you look at one of these, the one that we pulled out was just the 0th one, the first one that came out from iterating over this, right? So it only had, I'm approximating like 100 words, and then the rest was padded with zeros. And then these are the index of the first token, second token, and so on in this review that we had here. Okay, so we still have to encode these integers into vectors, so it won't quite work the way we have it here to input into an LSTM layer. So the simplest thing we can do is just do a simple one-hot encoding. So basically what we're doing is, for example, we're going to one-hot encode our first item here. So the result will be a vector of 20,000 elements where only one of them is a 1. So the one at index 10 will be a 1 and everything else will be a 0. We'll do that for all of these. So that ends up with a really big representation, which in this case is going to hurt our performance. But let's try that out. So the result, you'll see if we one-hot encode this input here, is now instead of having 600 integers, we've got 600 vectors of shape 20,000. And you'll see that, like, for example, the last ones here that were all, you know, the padding, the value at index 0 was a 1. So for all these vectors, only one of the values is a 1 from the one-hot code. There's an API change the textbook kind of shows just directly using this call, but you can't use that directly in the layer anymore. So you have to make a custom layer whose call method will call your TF1 hop. But that will allow us to create a model that will take one of these as input and output one of these, which is what we need to feed into, for example, like a recurrent neural network layer, right? So in this case, we're going to try a bidirectional LSTM recurrently. See how that works. So let's try it out and train the sequence model. So when that finally finishes, you'll notice two things if you have the patience to train this. So this model will take much more time to train than our previous ones. And I kind of hinted at that. That's because the inputs, oops, so you can see the desktop. So that's because the inputs are quite large. So each input sample is encoded. So each sample is encoded as 620,000 one-hot encoded vectors. Okay, so that's actually 12 million floats per each single movie review. And remember, we have tens of thousands of these in the training set and the validation set. So, you know, that's bad, both for how long it takes to train, but for the overall performance as well. It's kind of a big thing. So unless you have huge amounts of data, that's going to be troublesome. So you usually you see that was a pretty bad run there. So usually it'll be maybe close to the worst of the two previous models. But, you know, clearly there's some limitations to turning these into one-hot encodes, okay? So the simplest idea isn't great, so there's a better way. So let's talk about word embeddings. Okay, so that leads us to the topic of word embeddings, which is an important topic here. So when you do a one-hot encoding, you're basically assuming that different tokens are all completely independent of one another. Okay, so that's the assumption behind that encoding, right? And you know, this is true because the one-hot vectors, they're all orthogonal to one another, which means that they're completely independent. So in the case of words, I mean, that assumption is clearly wrong. Words form a structured space. You know, they're related to each other. They share information with each other. So, you know, words like movie and film are interchangeable. They should not be completely independent or orthogonal to each other. There should be some similarity in the vector that represents those words, not just completely, you know, a 1 for the index for film and a 1 for the index for movie, right? So, basically, the geometric relationship between two word vectors should reflect the semantic relationship. Okay, so we'd like to have it capture that similarity or even synonym. You know, film and movie are synonyms in lots of contexts. So in many ways, the one-hot encoding is not a reasonable vector space for the way words work in English and in most languages. Similar words should be encoded in similar vectors in the embedding space, right? And that's what word embeddings are. They're vector representations of words that achieve that. They map tokens in a human language into a structured geometric space that's not sparse, right? So like on the diagram over here, I mean, you can think of the one-hot encodings as things over here on the left, right? There's just a big sparse vector with one single 1 in there. So what we really want is a much denser representation. So in this case, each one of these columns here still represents a word, but it's not going to be sparse. I mean, there's going to be values that are 0, but values that are close to 1, or, if we normalize it from 0 to 1, we can normalize it different ways, and values in between. So each of the dimensions on here will be much lower dimensional than what we had over here, like typically like 100 or 200 dimensions instead of 10,000, 20,000. And the thing that can be learned for one of these word embeddings, each one of the dimensions tends to learn some kind of like an abstract concept. So as we'll see in an example here. So word embeddings were, used in natural language processing before deep learning. They were kind of a standard representation, but they're very important. In fact, they're one of the fundamental building blocks of like transformers in generative learning. Okay, so as we'll talk about later on, transformers use a kind of an attention model. The way that they're doing that is taking a word embedding like we have here and modifying the representations to add context to them. Okay, but that'll come up later in some future videos. So another example to try and build up your intuition about how an embedding space works like that. So let's say we have 4 words embedded in a 2-dimensional embedding space. Okay, so typically it's going to be 100, 200 dimensions, but we just have 2 dimensions in our embedding space. So like the same vector from dog to wolf, so this vector here is the exact same as, this is set up just as an illustration, but that's supposed to be the exact same vector from cat to tiger, right? So if I just took this vector and moved it over here, it would be the same vector in this 2-dimensional space, okay? That's because in an ideal embedding space, it's embedding a semantic. So we can interpret that. We can sometimes interpret these kinds of vectors as what they mean if we go and look at, if we're trying to visualize or figure this out. So in this case, that might be embedding the semantics from a pet version, pet canine to wild canine, and pet cat to wild cat has the same semantic relationship between these 2 items in this group here. Similarly, the vector, this example set up, the vector from dog to cat, compare that from wolf to tiger, is supposed to be a similar idea. So perhaps this is the semantics from canine to feline. So, just as some more examples, in real world embeddings that can be learned, so these can be learned in a similar way that a model can be learned for a neural network. So common examples of meaningful geometric transformations are things like a gender vector or plural vectors. So for instance, by adding something that means female version of semantic vector to the vector king, that will take us into the vector space for queen, right? So you can kind of find semantic vectors like that kind of represent gender transitions. So for particular words, that would lead you from the concept of king to its similar female gender version of queen. Okay, let's look at how to use an embedding space in practice. So there's kind of 2 ways, and we'll kind of look at both of these briefly here. So you can learn the word embeddings jointly while you're learning your main task, like a classification task on a text processing, whatever it is. So in this setup, you just start with a embedding space and you have all your representations initially random. And then as you're learning your classification task or whatever, in parallel, the embedding space is being learned to try and learn a good word embedding representation for the tokens in your space. Okay? Or you can use basically the same idea of using pre-trained models. So people have created these word embeddings on huge text corpuses, and sometimes it can be useful to reuse the word embeddings that they've come up with. Just exactly the same way that we reuse the convolutional hierarchy of features that were learned by convolutional neural networks. So So yeah, I mean, they're pre-computed using different machine learning tasks than the one you're solving, but you can bring those in and use those pre-trained word embeddings. But as we'll see, Keras has like libraries of models, pre-trained models for vision tasks, but it doesn't have like a corresponding one of word embedding. So usually you have to go and find the word embedding and download it yourself, and then load it in as a pre-trained, already set up word embedding space. Let's look at the first of these. So we can learn word embeddings jointly with our main task. So Keras, has an embedding layer that will create this kind of embedding for you. So you can pass your data through your network while it's learning the task to also learn the embeddings that it will use for representations of your tokens. Okay, so to use an embedding layer, so you should be kind of used to this API. Basically, you give it the input dimension. So this is max token. So this is, if we cut off at the 20,000 most frequent words, that's the same here. So same thing here. So we're saying that the embedding space, so we're going to embed our words into a 256 dimensional space, right? So we're going to have to end up with a representation for all 20,000 possible words in our vocabulary, where each single word in the number of whatever our vocabulary size is will have a vector with 256 dimensions in it, or 256 values in this 256 dimensional space. So that will be our word embedding, right? So again, instead of representing a token as a sparse 20,000 sized vector where only one of the values is 1, we're going to end up with, for one token, a vector that has 256 values, and those values are in this 256 dimensional space. And they should have a lot more, semantic meaning with all the other token vectors that get learned by this embedding space, right? So yeah, like the textbook said here, this is kind of how I understand it. It's best, these embedding layers are best understood as a dictionary again, but it's mapping the integer index. So the integer indexes are expected to come into here that stand for a specific word in your vocabulary up to the max tokens, which is 20,000 in our example here, to a dense vector, to a vector that has 256 dimensions. So it takes integers as input and looks up those integers in the internal dictionary. And it can learn a good embedding for the task in parallel. So, so once fully trained, the embedding space will have a lot of structure and a kind of structure that's going to be specific to your task. So that's one of the advantages of training your own word embedding space. Okay? So here's an example of a model, right? So here we're expecting just the raw integer sequence to come in, right? So since we pass in for our training data, the trained data set, so what comes in are those sequences of just the integer indexes. That's what the embedding layer expects to come in. But it's going to output, these come in batches, it's going to output the same sequence, but now each word is represented as a 256 dimensional vector in its embedding space when it outputs. So initially these will be random, but as we train it, this can, back propagation can come through this task here, and that can also be used to update the embedding to get better embeddings to lower the loss function. All right. So we're using a similar model that we did before, but we're not using the bag of words input with a 20,000 one-hot encoding. We're going to be using a sequence of these word embeddings to our LSTM bidirectional layer here. Okay, so let's see how that does. The first thing you'll notice if you train this model is that it's significantly faster than the last bag of words model that we did before, right? So the last one that we did, this is mostly because what we're trained with is much smaller, much more compact. So instead of these big 20,000 one-hot encoded vectors coming in as input, we've got the 256 dimensional vectors coming in. This was a particularly bad run on the test. I actually usually get above 86%, around 87%. But like I mentioned, we won't ever see any of these sequence models for this data set beat our best bag of words model. Right? But it usually should be in the range of at least the worst kind of bag of words model that we saw in the previous video. So there's another thing that can be hurting performance in these sequence-based models for text processing that's not turned on by default. I'm not certain why. I mean, I think you would usually just turn this on by default if you are doing a sequence-based text processing model. So remember, we talked about, we have to we have to have some sort of a maximum sequence length. And in this particular model, we're keeping reviews to 600 words. So I can't remember the average, but it was a little bit less than 600. 500 words or 400 words was the average review size. So some of them will fill out the whole thing, will be truncated. But a lot of them will be less than 600, sometimes significantly so. So you've got a lot of 100, 200, 300 words review, which means that everything has to have the same length when it comes into our recurrent layers, or the actual learning layers of our model here. So we have to pad anything that's too small with zeros. So like when we're using the bidirectional recurrent neural network, or even if we're just using a regular like LSTM with a single LSTM, so when it iterates through the inputs on the sequence, if it's been padded, like if it's only a 200 or 300 word review, it'll spend the last 300, 400 cycles getting zeros as input. So what happens on that is that the state just gradually fades out, and it doesn't do very good with those. It becomes kind of a meaningless input. So masking allows us to basically skip those iterations in the using the Keras API. Okay, so it kind of the Keras API kind of does this behind the scenes for you. And again, I'm not certain why it's not on by default, but you do have to enable that. But it's really easy to enable the masking for layers like this. So if you have an embedding layer, if you just ask for this mask 0 to be true, it will pass on these masks to layers after it, and those actually get passed through the rest of the layers, I believe. Right. So if we have input like this, so this represents 3 samples coming in. All of them are padded. Some just a little bit, some of them more or less. If you get the mask, the mask is going to have the same size as the input, but it'll be a Boolean array, an array of Booleans with true for the things where a recurrent layer should process, and false where it should stop. Right. So if you're using a bidirectional, it goes in the reverse. I assume that it'll since it's coming this way, this direction, it will skip over any falses until it gets to trues and start processing trues. So let's just add that on. So again, this isn't going to end up improving, but in lots of cases, this will make a difference. You usually do want to have this masking on when you're using recurrent layers. So go ahead and let that train. So usually when that's done training, you should find that it will probably improve the previous one a bit, although again, this is lower than I'm usually used to. But yeah, definitely won't be better than the best bag of words model that we've seen. So, okay, so let's move on to the second way of using an embedding space. So kind of like the transfer learning example that we talked about for convolutional networks, where you take the learned hierarchy of features, the base, you cut off the head and reuse those. So you can do a similar thing with word embedding. So you can take a word embedding that was trained on some big task. So this is, again, for the same reason, especially useful if your task doesn't have a lot of data. So you might want a more powerful word embedding, with the idea that a word embedding on a really big task might have general features that will transfer over to your task. Okay. So let's see if we can do that example here. So for one thing, there's no set of pre-trained word embedding models that you can just load in conveniently from the Keras API, at least not at the time of making this video, like there are for the pre-trained vision models that you can use. So as far as I know, most examples use this data set that we're going to use here, the glove one, or the big newsroom data set. There's probably lots of other word embeddings, but you do have to download the data and actually, if you're using Keras, load it into one of these Keras embedding layers, okay? So we're going to show how to do that here. So getting the data, like before, this is really too big for me to put into our repository for this class here, so you do have to download it. It looks like this particular data set, the website, they've let their certificate expire at the time of this video, so you might have to add in a no-check certificate in order to download the zip file. This is relatively big. In fact, when you extract it, the 300-dimensional version is about 1 gigabyte. Okay, so we're just going to use the 100-dimensional version. So after extracting that, I just removed the other ones to save space. Only kept the 100-dimensional one. We'll use that in our example here. It's but it's still like 500 megabytes or so. So also you might have problems running this example unless you have a good size memory on your computer system. All right. So these are just plain text files. So if you look at these, it's a text file with a word, so a string word, and then just a bunch of numbers which represent each of the values for, in our case, 100 dimensions. So using this text file, you'll have a word followed by 100 numbers that can be converted to floating point numbers, which represent the position of that vector representing that word in 100-dimensional space. So that'll take a little bit of time to load, actually. So when that loads, there's actually 400,000 words in this these word embeddings that we're going to be using here. So if you look closely at the code here that's parsing this, the first one, the split just splits off the first one from everything else. So the first one is a string word that we keep here in a dictionary, and then we convert all the coefficients to a NumPy array. Right, so we end up with a NumPy array, a vector of 100 values in this 100-dimensional space here. So we can pull it out. So for example, if we want to look up the word movie or film like we had before, that is actually its representation. So yeah, I believe these are all normalized to values between 0 and 1. But notice none of the dimensions are 0. So they all have something in this space, probably from negative 1 to 1. Or maybe, I should probably read about this, maybe looking at these, it's, yeah, so there's a value bigger than 1 here. So it's probably normalized to have a mean of 0 and a standard deviation of 1. So it had pretty big representation of a few of these. So a few of these dimensions, it was positive 2, negative 2. I mean, whatever ended up semantically being coded on those dimensions, this word had a lot of meaning in those dimensions. So what we need to reuse this in an embedding layer, so we can pass this in as a parameter for embedding layer, the learned word embedding space, but it needs to be a NumPy matrix of maximum words, right? So again, we're going to use the 20,000 most frequent words, and then, so every word is going to be embedded in a 100-dimensional embedding space, right? So 20,000 by 100 is the array that we have to create here. That's what we're doing here. So we have to do the reverse dictionary here. So we need something, given the index, that we can look up the embedding vector that's associated with that index. So that's what's happening here. I had a question about this. So, we're only using the top 20,000 of this. So since we have an index here, we can look up index 0, 1, 2, 3, so on. So I assume that the items were given indexes by their frequency of use, but that's something I should confirm. So I'm not certain if that's really working here or not, but that's the idea. So assuming that that's working, we're getting the 20,000 most frequent words of these 400,000 correctly here. We're basically going through these, going through our items one by one, and to create this embedding matrix that we're going to pass into our embedding that has that shape, max tokens by our embedding. So let's go ahead and let that run. Actually, a note on that is a little bit wrong. So yeah, looking at this a little bit closer, this is probably working right. So it's basically using the words from our vocabulary that we have in our text vectorization. So from that, we're getting the 20,000 words. So this has already been clipped to the 20,000 most frequent words in our vocabulary that we had. But then we're looking those up in this embedding index by the actual word. So this should work correctly now that I look at it a little bit more closely here. So finally, use a constant initializer to load the pre-trained embeddings. So basically here we're just loading that matrix that we created as the embedding, as the initializer. And it's also, we don't want those word embeddings to change when we're training a model, so we need to set this layer to be false for trainable, so they'll just be just looked up and not actually modified as part of the training process. Okay, so we're ready to go ahead and train. Okay, so we're just going to reuse that layer that we created with the pre-trained embeddings. So otherwise, it's the same models before. So we're not learning these embeddings in the embedding layer. We've frozen them. They're staying fixed. We'll just use the already learned word embeddings here. Go ahead and try this model out. So once training's done, you'll usually see that probably beats a little bit the previous model. Well, maybe not. So usually it'd be about the same. So the pre-trained embeddings here probably aren't going to be very helpful. The data set probably contained enough samples that it was possible to learn a good enough embedding on its own, so you get comparable results in either case. So again, while it doesn't really help too much here, it can be useful. So leveraging pre-trained embeddings can be very helpful when you're working with a smaller data set. Okay. Okay, so that's it for this video here. So kind of a quick summary. In the previous video and in this one, we were looking at the two basic ways that you can handle word ordering when you're doing text processing. So you can either use bag of words models that we concentrated on in the previous video, or sequence models, which we looked at in this video. So sequence models are going to process the words in the order they appear rather than as like a set of items, right? So for sequence models, the first thing we looked at is you can encode the sequence using one-hot encoding, like we would usually use multi-hot encoding for the bag of words approach to encode the vector that we need to pass in for input. But that ends up, so it's different than the bag of words because instead of having one multi-hot encoding, you need to have, like if your sequence length is 600, like we were using for our examples here, you end up with 600 of those vectors of 20,000 sparsely encoded. And it's completely sparse because you're doing a one-hot encoding in this case. So only one of the values is 1 for the particular word that came in at that point in the sequence, and everything else is 0. So that usually doesn't work very well. So instead, we talked about and introduced you to word embedding spaces. So this is generally one of the building blocks of transformers and generative AI. So you should understand word embedding spaces, okay? So they're vector representations of words that map human languages into a hopefully more structured geometric space, okay? So instead of being a sparse space, the dimensions in the space have semantic meanings usually if this word embedding is constructed well in a good way. Okay, so you can use Keras to learn your own embeddings simultaneously while you're training a model to do some sort of a text processing task, or you can use a type of transfer learning kind of similar to using the convolutional neural network layers that we did transfer learning from, you can use a pre-trained word embedding space and load that into a embedding layer for Keras. Okay. So that's it. I hope that helps you understand kind of the two different ways that you can kind of handle word order. In the next video, we're going to talk a little bit about transformers. So I hope you stick with me and come to the next video.